Am I just making it live also in YouTube?
Okay. Right now you are making it live.
Uh-huh.
Okay.
I mean, like it automatically Zoom integrates with YouTube, and in our channel it will be live streaming also.
Okay. Okay. So you can send me that link also later. The power supply power is there's a power problem with in my room. So I just changed the terminal to AC, moved AC, and then I connected my desktop there.
Okay, okay, okay.
Uh, So if power goes, then immediately everything will shut down. They are trying to fix the problem. Let's see.
Ritesh ji, let me start with the. Yeah. Ritesh, I think you stop your YouTube link in your browser. Ritesh, Ritesh, also you are muted. Yeah.
Okay, unmuted.
Right, right, right. Good. So now I'm getting a resound.
Sridhar, you start.
Sorry, actually it's in my browser. Sorry. So good morning all. I think we can start now. The time is 11:30. So hope everybody you're getting my voice clearly, right?
Yes,
Say
yes.
yeah. So good, cool. Okay. So knowledge is power, and knowledge shared is power multiplied. With this motive, we have initiated with a campaign of Let's Webinar, wherein HAW is going to organize 100 webinars in this year from now on the latest technologies and challenges involved by the industry experts. I'm very happy to see you part of the first webinar of this campaign, and my name is Sridhar Tokala. I'm the founder and CEO at HAEE. India will be a manufacturing hub for electrical vehicles in 5 years. Nitin Gadkari have said this news in the last month. India wants to become a global hub of manufacturing of electrical vehicles. Finance Minister Nirmala Sitharaman said in her budget speech earlier this month. The government seems to have two dominant objectives to control pollution and take the lead in an emerging industry. In spite of the government push, there are few technical challenges, that is battery technology, backing the motor and drive technology, charging and infrastructure, etc. We are very happy to be here on a virtual platform with Dr. Ritesh Keshri, who is a core technology expert in the EV segment. Let me give a brief introduction of his career. He have done his engineering and masters in electrical from NIT Jamshedpur in the year 2007. He got Young Researcher Fellowship from Ministry of University of Italy, first prize as a student team leader of the University of Padova in class 3 of Formula Electric and Hybrid in 2011. He have done his PhD in energy engineering from Department of Industrial Engineering, University of Padova, Italy in 2014. Since 2015, he is with Department of Electrical Engineering, Vishwesvaraya National Institute of Technology, Nagpur as an assistant professor. And 2016 Best Paper Award of IEEE Transaction on Industrial Electronics. His research interests include power electronics and drives for electrical vehicle propulsion and charging infrastructure. Dr. Keshri is associated with IEEE-IES and PELS and contributed as chairs for technical track and special sessions in IECON 2013-19. Dr. Keshri is contributing to Technical Committee on Transportation Electrification of Industrial Electronics Society IEEE as Chair of TCTE. With this brief introduction, I'll invite Dr. Keshri to take over the presentation. Keshri ji, you please.
Okay. Thank you, Sridhar, for my brief introduction.
Lengthy introduction,
Thank you
it's a
very much.
long back.
Okay. Yes. Uh, so, good morning to all participants. Uh, Actually, for this electric vehicle system, I'm working since 2008, and I started my work together with my supervisor, Professor Giuseppe Buja. And so you would be seeing that his name is here. And because we prepared this particular course for the students of University of Padova, uh, from that particular course, there was one segment to discuss about PMWC motor drive system. So this course was prepared for them. So my objective will be with you to discuss is that what exactly is a permanent magnet plus DC motor drive, why we are using it, okay, and then how we are going to control it for the light electric vehicle systems. So this will be my objective. Okay, and please feel free to ask the questions in between, or you can just type in your queries, and at the end of our discussion, I will pick each and every query. So don't worry about that, whether your questions will be answered or not. So we will try to answer all the questions to the extent whichever is possible. Okay. So just a moment. Okay. Okay. Okay, so what I suggest that like when you're talking about a drive system which is employed for the electric vehicle system, these are some suggested ratings. You can have a look on this one. Okay, in which like this paper is there in which we talk about electric machines and drives for the electric and hybrid electric vehicles, then motor generator and traction for propulsion system. Then there's one book by Pmbl. This is really good book, and so here you can find all about the basics of permanent magnet machines. Okay. Then there's one overview of permanent magnet brushless drives. This is again for the electric vehicle. And then we have carried out some analytical work related with Pmbl motor, relating the torque and the speed characteristic. So that I also keep in the suggested references. So you can go through these references. Okay, next. Okay, so before we start, we have to understand that first thing is that we talk about the e-mobility. What exactly is the e-mobility? So when we talk about e-mobility, it automatically concerned about the automotive system or the system which is applied for the motion control or transportation. So in e-mobility, basically we talk about onboard power electronic systems and the related control which is employed for the transportation purpose. And second thing is not only that you need to have the tractive power, but the system which is also employed for the energy exchange between the vehicle and the grid. Because when we talk about the electric vehicle, then you need energy to charge the onboard batteries. So you have to receive the energy from the grid. And at another time, maybe like you would be interested in submitting this energy to the grid. So it is vehicle to grid and grid to vehicle. And maybe like you would also be willing to exchange the energy between the two vehicles. Okay. So that also comes under the category of e-mobility. And the next category, what is like whatever the communication system which is employed to take care of the overall control of the system within the vehicle and between the vehicles and with the vehicle and the central monitoring stations. So all those things comes under the category of e-mobility. You can say, okay. So let's a little more in depth, like what exactly is the definition of an electric vehicle? Okay, this is the definition we're talking about. So it is good to first read it and then I explain you. So a vehicle is termed as an electric vehicle if it uses electric motors to drive the wheels directly or through differential gears. Understand? And by receiving energy either fully contributed by the onboard DC source. It is important. Or either you get hold of the energy from the onboard DC source, or it is contributed in part by the lower sized IC engine. Means your IC engine could be there definitely, but the size of that IC engine will be less. Means you will be receiving a portion of the energy to assist your onboard batteries. Okay. So that's why it is the lower side IC engine. Or in some cases, you would be using IC engine to give the tractive power to the vehicle. Okay. So for that, we have different architectures, like people say series architecture, then parallel architecture, then series parallel complex. So we receive energy from we can also receive energy from the IC engine as compared to the conventional. You see that IC based vehicle. You see that the size of that IC engine, what you're going to use in case of an electric vehicle to assist your onboard batteries or direct get some portion of the torque which is required for the propulsion. Okay, that will be always lesser than the conventional IC engine. And then what is the objective? Only objective, or the important objective, is that we have to improve the performance. We need improvement in the performance and reduced emission. This is the, so whatever we are doing in the area of automotive technology, our objective is that we want that we must have a very good performance, means efficiency should be better, and then what is the main objective? We want to reduce the emission. So this is what the electric vehicle system is there. So in electric vehicle, basically, you see that the important term is the electric motors. So the concept is that if you are giving a final tractive power, whichever is required for the vehicle, through the electric motor, then definitely it will be an electric motor. Sorry, it will be termed as an electric vehicle. Okay, then let's understand something. Let me raise it this. Okay, so like we see that in the conventional case, we are having, let's say that this is a fuel tank. Okay, I'm writing FT. Then we are having, this is powering with IC engine vehicle. And then we have shaft. Okay, and this shaft is connected with the differential gear system, DJ. And then to this, with this differential gear system, we are having wheels of the vehicle. So you see that all the transmission, what you are seeing is the mechanical one. And we know that there is huge loss in the mechanical transmission. So then what you can do here, so here you see that the performance is deteriorated, efficiency is low. Okay, and because the losses are there, so to overcome those losses, you are going to consume more fuel. This is the thing. You can use another configuration. Let's say that with the same IC engine, this is fuel tank, then you are having IC engine, and with this IC engine, your generator is coupled. Okay, it is generating electrical energy, and then this is a wire. Understand? This is a wire connectivity. You can say wire connectivity, and then you are having, let's say, some power electronic arrangement will be there. So I'm making it bigger, definitely. And then you are having a DC bus, let's say. Okay, DC bus, and to this DC bus, your inverters are connected. VSI is connected, and this VSI is powering to your motor. Let's say I write M, and this motor is coupled with now your differential gear, and then your wheels are there. Then your wheels are there. So what happens here, that you reduced this much of whatever the losses were there here with a most efficient system after this one. So automatically you are increasing the efficiency of the system. So because now your system has become efficient, so you are going to consume less fuel here. So definitely this is also an electric vehicle. Why? Because you are giving final tractive power through an electric motor. But the source from what we are using, the source is your gasoline, which is not allowed for us. We don't want to use it. So what are the possible solutions then? So in electric vehicle, other solutions are that you can use battery. Okay, you can use battery, onboard battery, and to this battery, like you see that, let's say that this is forming a DC bus here, and then we are going to use the same arrangement here. Now you are having voltage source inverters which are connected here, and then you are having motor. Okay, and then this motor is connected with a differential gear, and you are now powering to the wheels. You see, this is the situation. So, but what we are talking at present is about this system as an electric vehicle, because you see that either you can use gasoline, or you can use batteries, or you can use the combination of these two. You're seeing this one, okay? You can use the combination of these two. Understand? Forming the common bus. Means after this, maybe it will not be there. Understand? So you see that you have a gasoline, IC engine also, and the battery also. This is the case, which is available. But here also you see that the final tractive power is being given through the motor. So it's an electric vehicle. And of course, here this IC engine will be lower in size, because now you are going to use the most of the power from the battery. Okay. Most of the power you are going to use it from the battery. Okay. So this is the situation. So in this case, you will see that the efficiency of the system will be more. So this arrangement, what you are observing at present, this one, it is termed as hybrid electric vehicle. Okay. So when in your system, you see that when only battery is there, this system is not there, then it is called pure electric vehicle. This configuration is called pure electric vehicle. Yet there is, because your main source of energy is only battery, and you are not getting energy from anywhere. Okay, this is called pure electric vehicle. But when you combine this, okay, this becomes this IC engine coupled with the generated electricity, that common bus to the power electronic arrangement, to the common bus and battery. So it becomes the case of hybrid electric vehicle. So I hope you understand what is the meaning of this one. Then you will be seeing other configuration also, because you see that the definition we have used the term motor is connected to power is transferred to the wheels directly or indirectly. Directly means this is the indirectly means through the differential gear. Okay. In what is the meaning of directly means you are having a wheels. You see, you are having the wheels, and to this wheel, this motor is there. Understand? This motor is there. Motor is connected here. Okay. And then you are having voltage source inverters. Here I am making the diagram. I hope you understand before that what it was. So this may be like feeding this one, or okay. With the single inverter is drawing the two motors, and this is the wheel. So this type of configuration is called in-wheel motor. Okay, in-wheel motor, in which your motor is embedded into the wheels. Okay, here I am showing that the voltage source inverter, same in voltage source inverter is feeding the wheels. Okay. You can use different inverters also, generally, which is the practice. Like the two different inverters will be there to operate these two vehicles. Okay, and if you are using single inverter, then you have to prefer that differential gear arrangement. Okay. Now, let's see here. So I hope you understand the definition. This is what I explained you. If your vehicle is running with pure battery, then it is called pure electric vehicle. Only battery, then it is termed as pure electric vehicle or battery electric vehicle. And if whole of the energy is required for the traction is contributed by the onboard source. Understand? And it is termed as hybrid electric vehicle if a part of the energy of the for the traction is contributed by the IC engine. Then what is the drive? Because here we are going to talk about the drive. So an electric drive which uses a Pmbl AC motor. Okay, for electromechanical energy conversion is called a permanent magnet DC motor. If you are using an induction motor, then it will be an induction motor drive. Okay, let's say in common you use, let's say, synchronous motor, it will be a synchronous motor drive. So which motor you are going to use for the traction purpose, okay, or drive application, the drive name will be based on that. Let's go ahead. Just a minute. Okay. Okay. Now let's see what is the total electric vehicle system is there. So here we generally say that electric vehicle propulsion system. Okay. And different components, what we observe is the supply system. Okay. This is the supply system. Then we are having a traction system. And then we have a control and monitoring system. This is there. Okay, these are the main parts which are on board the vehicle. Then you can see that other parts also. You can see the other part. And what is that other part? The interface of this electric vehicle, whatever the electric vehicle is there, with the grid. Okay, with the grid. So this is the grid. Then maybe like you will be using some circuital arrangement. So I'm just writing here circuital arrangement. Just a moment. I think there's some issue. Just It's okay now. So some circuital arrangement, and then this circuit, and this will what? It will be a AC to DC conversion. And then finally, you are going to submit the energy to the vehicle. So this system is called charging system. Okay, this is called charging system. Charging system. It could be conductive if you are directly, it is connected to the vehicle with a wire, or it could be wireless also if you are not using the wire. So this is there. And then, so these are the systems: supply system, traction system, control and monitoring system, and then charging system or charging infrastructure. These are the different components of an electric vehicle. Okay. Then let's see that what is there in the supply system. In the supply system, you will find that different possible energy sources are there. So what are the different energy sources are there? It could be your battery. It could be your, let's say, fuel cell. Okay. It could be photovoltaic panel also, or it could be ultra capacitors. Understand? So out which a battery, fuel cell, photovoltaic, these are called energy sources. Okay. And then ultra capacitor or flywheel, what you're going to use, these are power sources. These are power sources. Understand? So what you will see in practice that like here, you will be seeing that either this, let's say suppose the battery is there, so battery will be just connected in series. Okay. And if you are not intended to get a get back the regenerative energy, so under that situation, we will not be using any circuital arrangement here. Okay. This arrangement will not be there. But suppose that you will be using sources such like a fuel cell or photovoltaic panel. Understand? Under such a situation, because their output characteristic changes, okay, with the load condition and the input, like in case of photovoltaic panel, whatever the solar insolation is available, because the output characteristic is changing. So to maintain a particular operating point, okay, we need to use this type of circuital arrangement. You can say that it could be a boost converter, DC to DC boost converter. If like a bidirectional power flow feasibility is there, then we can use bidirectional power flow. But in case of fuel cell and photovoltaic panel, that is not possible. Okay, so this is what it is about supply system. Okay, let us go towards our main agenda. Okay, because I'm not going to discussing much more about the supply system. We can discuss it later also, but main agenda is the traction system. So what is the traction system here? So traction system, it consists of your traction motor, okay, together with a voltage source inverter. Okay, traction motor together with voltage source inverter plus VSI. This is termed as a traction system. Okay, but please wait here. Okay, suppose that it depends upon which type of traction motor you are using. If you see here, like we are showing that it is using a three-phase supply, definitely it is AC type. Okay, so under such type of motor, VSI will be used definitely. Okay, but if in place of this traction motor, like AC type traction motor, if you use a DC motor, let's say, okay, DC motor, so under this situation, it will not be a voltage source inverter, rather it will be a DC to DC converter. Understand? DC to DC converter. So when you are working with a DC motor drive for the traction purpose, it will be a DC motor together with a DC to DC converter. Understand? DC to DC converter will be termed as a traction system. And then rest see, we are talking about here we are talking about traction system, which is employed for the motion control. So we need a control and monitoring system also. It is not like that we have to run at the constant speed. So for that purpose, we need a control and monitoring system in which like you will be having different sensors, which will be getting information from the maybe the motor, what is the current flowing through there, so what is the terminal voltage, depend upon which type of control you want, current control, voltage control. And then maybe like you'd be interested in knowing what is the status of this DC bus, whether it is regulated or it is, whether it is like what it is desired or not. Okay. Or if it is going beyond the desired limit, then you have to make the control. So all those purposes need sensors here. And all those sensor information will be going to your control system, where based on your reference, you will be taking the action. So this is what it is about control and monitoring system is there. Okay, it's like this is the most basic operation of the control and monitoring system. But like you can have other work of also the control and monitoring system. Maybe like some communication is required. So all those things can be also part of this system. Okay. Let's see. Okay. Then I told you that we are using the term traction motor. That like is the all the motors can be considered as a traction motor? No. There are some criteria. Okay. What are the criteria? The criteria is that like you can see that these are some criteria. Okay. 7 criteria are there for a motor to qualify as a traction motor. The very first thing is that that motor, what you are going to use, it must have a high torque and power density. What exactly is the meaning of high torque and power density? I explain you. Suppose that you are having two motor. This is one motor and this is second motor. I'm writing here M1 and M2. And we say that this M1 is having high, it is having high torque and power density. Understand? So its meaning is that, let's say that both are of 1 kilowatt for the time being. This is also, so if the torque and power density of this motor is high, M1 is higher, then from the size point of view, this M1 will be, sorry, just a moment, M1 will be smaller in size and M2 will be larger in size. This is what we can explain here. For the same time, if M1 is having high torque and power density, it will be compact. Compactness must be there. Okay. Now, let's see second one. Then the second point is that high starting torque for low speed and high power for high speed cruising. So to understand this one, we can consider the very famous diagram which we always use. Remember this one, that here it is speed and here it is torque. So what happens that you see that it is a constant torque zone of operation and this is a constant power zone of operation. And this particular speed is our, I'm writing here omega rated. Okay, and this is the torque, maximum torque. Okay, this is the very famous what we have seen. So when we talk, and we also know that the power variation will be here, like you can make the power variation like this. Okay, and then after it works in the constant power zone. Okay, so this zone is constant power zone, and this one is constant torque zone, constant torque zone. Okay, this is there. Now, let's see here. So what it is saying that a motor to qualify as a traction motor, it must have high starting torque. We need high starting torque because you remember that like when we are having a vehicle, okay, so this vehicle, when you are going to start it, okay, it has to overcome with a different torques. A low torque can have different components, maybe one is that very famous tractive situation is this one. I hope you remember this one. Okay. So starting torque, this one is that speed. When the speed is low, you need very high torque to start the machine. And then as you increase the speed, the torque requirement reduces. Okay. So this is a particular speed torque characteristic of a tractive load which is used for the tractive purpose. Okay. So this is the requirement. So if your machine is capable of giving higher torque during this time when you are just starting, so it is very good. So that's why we need high starting torque, because your vehicle is like, when we talk about a light electric vehicle system, then all light electric vehicle systems are those those vehicles which are having the mobility in a small city. Understand? A small city. Mid-duty vehicles are those which are like car and etc. Like their mobility is in between either longer run or in between the two cities. And heavy-duty vehicles are those like which need to continue for the longer duration, like trucks and other duration, long range. Understand? So those vehicles which are running in the city, we can understand that a rush is there. So always you need to stop and again you have to start it. Okay, so you need high torque to, always high torque to overcome this. So that's why you need high starting torque. And what about this high power or high speed cruising? So let us consider the situation. Okay, let us consider the situation. Let's say this one, that we are having a machine in which this is the okay, but the characteristic is something like this. Let's say that this is the situation. This is one and this is second one, in which case it will be possible to run for the longer range, range will be more. Definitely in this case, because here you have the higher power. Okay, higher power. So you will be able to cruise at high speed with this high power. So this is required. If it is like this, it is very good for you. Okay, so always this will be considered as better because here you are having high power. So it is possible for you to that you can go for the higher speed. Like you see, these are falling down, but here the machine with this characteristic will be running more. Now, second thing is that next is the next characteristic is there wide speed range with a constant power operating region. This is the constant power operating region. 3 to 4 times the base speed. What is the base speed? This one. So let's say we talk about that we are able to run our machine up till this one. So that this, let's say that this is the maximum speed what we can achieve. So this maximum speed should be 3 to 4 times higher than that rated speed than this one. Understand? This is what it is talking about. Okay. Then next is that high efficiency over wide speed and torque range, including the low. Like you must have your traction motor must have the higher efficiency here also, and higher efficiency when you are operating in this range also. Then next it is talking about intermittent overload capability. What is the meaning of it? When you are going to accelerate it, okay, so you need high torque for the acceleration purpose. So let's say that intermittent is like, basically we are talking about this one. So suppose that your motor is having the nominal torque, let's say 10 Newton meter. And when you want to accelerate it, you should be able to deliver high torque, let's say 20 Newton meter, let's say, at least 2 times. Okay, typically twice, 2 times for the acceleration. So you are going to accelerate your vehicle. So this is what we are understanding. So for a very short duration of time, your motor should be able to deliver twice the rated torque. Understand? 20. Of course, let's say that in this case, your motor is drawing 10 ampere. In this, it will be drawing 20 ampere. The current will be higher. So this situation is basically limited by the thermal capability of the system. Like the winding, how much heat would be generated, what is the thermal capability of the wheels which are being used, everything, tire. Okay, and then reliability and all these things are must, and then cost, of course, we always look for the cost. Okay, and then what are the different candidates for the traction motor? Traction motor, it is induction motor, of course, because we have a high efficiency inverter motors, induction motors are available, so those are the candidates. Okay, then switch reluctance motor, which is also like we say SRM machine. Then permanent magnet, brushless machines, and then next one is that nowadays this is also being explored, synchronous reluctance motor. So all these are the different candidates, out of which this induction motor, switch reluctance motor, and synchronous reluctance motor are non-permanent magnet machines. Understand? But of course, as its a name is here, permanent magnet brushless machines. So there you need permanent magnet. But of course, the torque performance what we are going to get is much higher in this case because of the higher flux density. Okay, so all motors have that. Like it is not like that you cannot use this induction motor as parameter for all the ranges, for light, mid, and heavy duty vehicles. You can use any of this motor in any place. Okay, but there are some limitations where they give the very good performance. Like if you go for more than 150 watt kilowatt application, 150 kilowatt induction motor is the only solution. Okay, the Pmbl motors, like permanent magnet brushless machine, it has two components. We will see Pmbldc and Pmblac type. So this will go up to 2 kilowatt. Okay, and this will, you can go, let's say 30 kilowatt higher. Understand? But here it is only for 2 kilowatt. So each motor is having some capabilities. Another thing is that in SRM machine, switch reluctance machine, the one like common issue what we face, that it receives the energy from the source in bulk. Understand? So we find huge pulsation in the torque there, and the pulsation in the input supply also. So the life of the battery also gets destroyed. So to overcome that, you need input filters also. So sizing, but people have tried to solve that problem also. But that issue is not with the synchronous reluctance machine. So this may be the future candidate for the electric vehicles. Okay. So, but today, like we are going to we are discussing only about permanent magnet brushless machines. Okay. Okay. So before we go ahead, because I have used the term permanent magnet brushless machine, so like generally people get confused about here what exactly it is. Like, because the people, very common word, people will be seeing that it is PM BLDC, and mostly people will be saying that it is a BLDC motor. Only BLDC motor term will be there. People will know. Only BLDC people will say. So people get confused whether it is a DC motor or AC. Okay. So let's see here. Let's see here. So you know about the BLDC DC motor. We have seen the DC motor. So I'm just drawing a rough diagram. This like this one, and then we have the excitation like this one. So I'm making a random. We are having this one. So these were the field. Let's say north, south, like this is made. Okay, this is the DC motor. And what you are doing, you are giving the using a soft magnets here to make that convert it electromagnet when you excite. These are the basically field, and here is your armature. So if you replace this part, understand? If you replace this part, once again I'm making here. This is a DC motor. Please remember. Okay, this is a DC motor. That here you can make the process for that your armature. This is armature, and this one is, let's say I'm writing field FM. Okay, so but in place of this one, if you just remove this field winding and you put the permanent magnet north south like this one, and then you are having rotor. So you see that you have removed the field winding. So this is still a DC motor, and now you do not have any field winding here, but you have used a magnets which are going to create the field flux. Okay, so this is called PMDC. Okay, permanent magnet DC machine. Understand? Then what is BLDC? Basically, BLDC is a synchronous motor. Okay, so just see the configuration of a synchronous motor. So in what we have studied in synchronous machine, you say that it is represented like, I'm just drawing a basic diagram. Okay, basic diagram, and then we have three-phase winding. Here I am representing it as a concentrated winding. Just means I'm representing it. Okay, and then what happens here, that this rotor gets excited with a DC supply plus and minus. So what happens here, when you give a DC supply here, this is AC. Okay, DC supply, this gets converted into an electromagnet. Okay, and then it produces a flux here, rotor flux. Understand? So this is what it is, your synchronous motor. Now, in place of this one, if you make it like this, okay, now you remove this part, understand? And in place of that, you use a permanent magnet, let's say north south, and then you have the three-phase supply here, three-phase supply here. Understand? You have the three-phase supply like this here. So now, because this correction, how we are giving this correction through the process. Exciting that rotor to the buses. So because now you are not using any brush, so it becomes brushless. Okay, so this is represented as BL. Okay, and now what you have used? A permanent magnet. This is a permanent magnet. So this type of machine is called permanent magnet brushless machine. So the general term is PMBL. It is called permanent magnet brushless machine. Now, next, then, and people in general say it as permanent magnet synchronous machine also, PMSM. But please wait here. PMSM has a different, when we say PMSM, people understand with a different category of the motor of same PMBM, permanent magnet brushless. Now, there are further classification. If this PMBL, permanent magnet, the winding what you are seeing here, okay, here we have not shown the winding, but in practice, you see that how we make that, we have the slots like this, okay, in the stator. In this diagram, I have made the representation like this, but the winding is like this. If this stator winding, okay, like this. If this stator winding is distributed in nature, understand, like induction motor, distributed in nature, distributed winding, then the back EMF, because of this permanent magnet, with the flux which is going to link with the windings, okay, that will be sinusoidal in nature. Understand? Sinusoidal in nature. So when the back EMF of the winding is sinusoidal in nature, it is termed as permanent magnet brushless AC machine. Okay, and this is in general termed as PMSM also. People say that, okay, but please be precise. It is PMBL AC machine. Okay. Okay. Just a moment. Just a moment. Huh? Hello, Vilas. Huh? 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 हाँ, तो ठीक है ना, मेरा सप्लाई यहाँ से चेंज कर दीजिए, वही बेहतर होगा। अच्छा, ठीक है, तो मैम से बात कर लीजिए ना, हम थोड़ा मीटिंग में हैं। हाँ, ठीक है, ओके ओके, sorry for the interruption. And if this winding is made like a concentrated type, okay, if you make that winding as a concentrated type winding, okay, just like in the case of DC motor, like here what you are making, understand, then you will see that the back EMF which is induced in the winding, this stator winding, it will be trapezoidal in nature. Okay, it will be trapezoidal in nature. Okay, this is the difference what we see. So this is when it is like this, it is termed as PMBL DC motor. Understand? So what BLDC we are talking about, it is this BLDC. Understand? It is not this one. We are talking about this BLDC motor where it is a synchronous motor and the winding is concentrated type and rotor is replaced with a permanent magnet. So this is what a PMBLDC motor. And later again you will understand that why this is called PMBLDC motor, because the torque characteristic what you are getting is just similar to the DC motor. That's why it is we give the name BLDC. Understand? Okay. Okay. One thing I also want to explain you, like you will not find like this, you will be seeing the two ideal situation. Either your motor is extreme cases, back of is trapezoidal in nature or sinusoidal in nature. So it will be BLDC. I write here PMBLDC, and it will be PMBLAC. Okay, of course, that design consideration and the winding will be there. So you will not find that the machine have pure trapezoidal or pure sinusoidal. So there's a possibility that the configuration will be in between these two. Okay, in between this one. If the behavior is more close to the trapezoidal behavior, we say it is a PMBLDC. If the behavior is more close to that sinusoidal, then we say it is a PMBLDC. Okay. So let's go again back to our slide. So I hope you understand that what exactly is the BLDC motor. It is a synchronous motor. Okay. and which is having a rotor as a permanent magnet and a winding is concentrated type. Okay. Let's go ahead. So this is the layout of a electric vehicle in which the BLDC motor is being used. Okay, so you can see that the supply system at present we are not discussing about, but here in this case we are having a supply system in which the 4 batteries are used. Each battery is of 12 volt, 12 volt, 12 volt, and 12 volt. Means all are connected in series. So the bus voltage is 48 volt. Means the batteries are connected in series. Okay. Each is 12 volt, 12 volt, 12 volt, and 12 volt. This is like this one. Understand? Then your traction motor, you see that this motor is embedded inside the wheel. So it is a wheel motor, hub motor, generally we say. If you open it and go inside, okay, go inside here, you can see here this diagram. I just zoom it. Okay, I just zoom it here so that you can see here. So you can see that this is a BLDC motor. You open it, and then this is the state of winding, what you are seeing. And these slots, what you are observing here, this slot. This is not these things. These are the permanent magnets. These are the permanent magnets. Okay, and in this position, what you are seeing, this is the Hall sensor. Hall sensor, which looks like here. You see. So you're seeing that all are here, but actually they are 120-degree displaced in electrical space. Let me zoom back it. Zoom out. Okay. So rotors are here. You see that these Hall sensors are 120-degree displaced. Okay, from each other, electrical space. And then we have a voltage source inverter. This is VSI. Okay, and this is the interface circuitry, DSP interface, a micro TMS processor, what we have used for the control. Okay, this is there. So you have a traction system, then control unit here. In the control unit, you will be giving a torque reference. Okay, and then based on that torque reference and the feedback from the Hall sensor, which need information of rotor. Please remember that this is a synchronous motor. Okay, so you must know what is the rotor position, and according to the rotor position you will be injecting the current. So to inject the current, you will be deciding what are the gate pulses to these switches: S1, S3, S3, S5, S2, S4, S6. So what the sequence is, what the gate pulses you are giving to the switches, that must be synchronized with the rotor position. Then only you will be operating your machine, otherwise you will not be able to operate. Okay, so this is what the schematic of a you see the pictorial representation or a view of an electric vehicle drive system, Pmbl drive system. Okay, then what are the different classification? Because now we are going into Pmbl motor. Okay, you see that you will be seeing that Pmbl motor, permanent magnet brushless machine, basically we say that can be having a radial fill, axial, or linear. Radial is what? You see that, suppose that this is the motor. Okay, this is the motor, and your shaft is like this. This is the shaft. So this is the radial direction for the shaft. This is the shaft. Okay, and we are looking from here. This is that view. Okay, so if the field is axial, you see that this is north and this is south. It is axial coming back. Okay, it is axial. This is axial moving like this one. This is called radial. Sorry, not axial, radial. Radially outward. This is radial. Radial. So it is called radial field machine. Okay, but if the flux is going to move like this one, like here in this case, okay, here you see that it is along the axis of that shaft. Along there. So this is called axial field machine. And then linear, you see that in both the stator and rotor, you see that it is remains linear. So it is a linear field. And but there's a possibility that you can have the combination of these two also. Okay, or combination of these, all these three will be there. So that's a like a complex type of structure is there. Okay, next is there. Now, as I explained you that depending upon which type of winding you're using, your back EMF can be trapezoidal. It can be trapezoidal, as I explained you, or it could be sinusoidal. We have three different back EMFs are shown because it is corresponding to three different phases of the motor, three phases. Okay, so when it is there, it is termed as PM Bldc. It is termed as PM Blac. I explained you. Okay. Next, let's go ahead. Okay, then further you will see that how the magnet is mounted. Depending upon that, we say that it is a which type of machine. So it will be surface mounted. It is termed as also surface mounted permanent magnet process motor. Why? Because in this case, the magnets will be mounted on the surface. You see, so it is surface mounted. There's a possibility that surface magnets will be buried on. It will be on the surface of the rotor, but it is buried here. So it is surface inset. So these two, surface mounted or surface inset, this comes under the category of PMBLEC, used for PMBLEC motor. And another structure you will be seeing that, like, remember that in this case you can go up to 2 kilowatt. Okay, not more than 2 kilowatt. Then other structure is that you will be seeing that a rotor is like this, magnets are like this. Okay, they are buried inside this one. This is a rotor and the magnets are this. So these are called interior permanent magnet. And they have what? The benefit of is what? They can be run at a very high speed. And they comes in, they are good and they are used for Pmbl AC machine, or simply say that PMSM. In PMSM machine, you will see that the power is more than 2 kilowatt. When we say 2 kilowatt, it is nominal power, not the peak power. Peak power is 4 kilowatt. Okay. Next. Okay, then we have to see the electrical structure, how the permanent magnet is placed. You see that here, that permanent arc, this is arc, and this is the permanent magnet here. Okay, and this is the another one. So when the permanent magnet arc is 180 degree, okay, it is 180 degree electrical duration, then it is called 180 degree arc magnet. When the permanent magnet is placed here for 120 degree only, okay, then it is called 120 degree arc magnet. This is from book of T.J. Miller. Okay, this is called 120 degree arc magnet. Then what is the difference? When you are going to use 180 degree arc magnet, your stator winding will be star connected. Okay, star connected. Stator winding. When you are going to use 120 degree arc magnet, your stator winding will be delta connected. Okay, it will be delta connected. It will be delta connected. Difference is that this one is used for the very low power application, maybe for the printers and other things. Okay, but this is used for the traction. Because in this case, you see that at a time all the three windings are going to contact, so losses will be more. Okay, but in this case, you will be seeing that the only two phases conduct at a time, either this one or this one or this one, like this one. Only two phases. So losses will be less in this case. Okay. So 180 degree arc magnet, 120 degree arc magnet. Now, when it is this case, then you will be seeing that the phase current is, which is injected, is of 120 degree flight direction. Okay, 120 degree flight direction. Phase current. Okay. Current what you are injecting here. IA, IE, and IC. That will be 120 degree direction. Okay, but in this case, the current what you are injecting, okay, what you are injecting here, IA, IB, and IC here. So this what it is going on. Okay, we are concerned with this. Okay, this duration, this will be this inside, not outward. It will be like 120 degree. sorry, 180 degree arc. This is a 180 degree arc. But if we talk about the current which is flowing here, IAB, understand this is A phase and this is AB, it will be again 120 degree duration. Understand? So from the control point of view, there's no difference. Okay. Whatever the control is here, same control will be working for this one. Let's see further. Okay. Very important thing that because this is a synchronous motor, I explained you that we always inject the current which is synchronized with the flat top portion of the back EMF, flat top portion of the back EMF. Okay, so the current, this is the trapezoidal back EMF. The current which is injected is synchronized with the flat top portion. Why we are doing so? Because when you do like this, synchronized with the flat top portion, it is going to ensure you the maximum torque per ampere. So this is EI, and this is, you see that minus I minus E. So EI and EI to EI. Okay. So this is the arrangement, like phase back EMFs are displaced from each other by 120 degree, and the current is also displaced from each other by 120 degree. Okay, you see. So this is our requirement. And now to do this one, we have to see how we are going to do it. Okay, so this is circuital arrangement of a Pmbl motor. I will explain you this also. Okay, so this part I don't explain you, rather I directly explain you like why we need the synchronization. So we can consider 180 degree arc magnet here, what you are seeing here, arc magnet, what you are seeing here can be replaced by a bar magnet. Okay, and the stator winding, what you are giving the excitation, can be considered as electromagnet. This one. Okay. Phase A, phase B, and phase C. When you reverse the direction, so when the positive direction you are considering the fluxes, you will be phi A, phi B, and it will be phi C. Okay, and when you will reverse the direction of the current, the injection, okay, you will be seeing that here next better. So the next slide, that it is a phi A, phi B, and you will be seeing here that it is minus phi A minus, phi B minus, and phi C minus. So total, these are the flux vectors. We don't go in much detail. Okay, so but here you see that this is phase A and this is phase B, because at a time two phases are conducting. So your stator flux is like this one. So torque will be produced when this will get interacted with the rotor flux. Okay, let's see. So this is the like the different 6 different vectors are available. Here it explains like why it is necessary to. The thing is that suppose that you give a phase A current as a positive current and phase B negative one. So this is the situation. Your stator flux is in this direction. In this direction. Okay. And here is the rotor. So what it will do, it will try to catch this one. Okay. So it moved like this one. Now, if you don't give any further excitation, if you don't change it to further, then what will happen? It will remain in this position. It will remain in this position. Understand? It is not going to change it. So, but you need to move it. So what you have to do, you have to change this position. Okay, excitation you have to change. So how we have done it, you see. Okay. Sridhar, there was some problem.
No, I just muted. So now it's okay.
Okay. This is phi S. Okay, this side it is. So what happened again? This is the rotor flux. Again, it will try to catch it. This is rotor and this is stator. It will try to catch it. So it goes and stuck here. Again, you have to change it. So now I just pass the slide so that you can understand the situation. You see, just a moment. Okay. Okay, you can see that we are changing the excitation and it's a rotor is rotating. We can go back, you can see. So it is very important for us That you keep on changing the excitation as per the rotor position. So this is a synchronous machine. Okay. Now, next objective is what? We have to operate this machine. Okay. How we are going to operate? This is synchronous machine. So we must have to know what is the rotor position. And then accordingly, we are going to inject it. So first objective is to find out the rotor position. Okay. So what you can do that you can just take out the back EMF and the Hall sensors output. Just observe it. So this is the back EMF. This is the back EMF. And if you see that the Hall sensor position information is like this, but please wait here. Okay, what the magnet you're using? You're using 180-degree arc magnet. You're using 180-degree arc magnet. So that, and you have the Hall sensors. So when the south pole approaches the Hall, then what happens? It becomes high. Understand? And it continues until the North Pole approaches. When the North Pole approaches it, it becomes reset and remains zero, like this one. Okay, here is the situation. But please wait that it is an arc, it is moving, you see. So you will not see such type of behavior. You will not see such type of behavior. So which type of behavior we see? I just show you. So under such a situation, you will be seeing that the Hall output is not like this, rather it is like this. Understand? And you will see in your oscilloscope, you will find that this is 0, this is 180-degree, and this is 360-degree. And again, in the next cycle, it will start. But we see that our requirement is not this one. We will not be able to work with this. So you have to use edge detector circuitry. Okay, so when you use this edge detector circuit, what will happen? Whenever the positive edge is detected, like this one, you will get a high. Okay, and it will remain it like this. So you have to use a circuital arrangement to convert this into this type of behavior. Otherwise, how you're going to use it? It is difficult. Okay, so you have to use edge detection circuit. Okay, this is the situation. So this is what we have seen there. Okay, it is not like that we are getting the actual behavior is like this. Actual behavior is like this. Understand? Actual behavior is like that, but we have converted it. So now, how many Hall sensors are there? You see, you are having 3 Hall sensors. Okay, A, B, and C. Okay, so you can check the position. Like this is high, this is low, and this is high. Here it is high, this is low, and this is low. This is high, this is high, this is low, this is low, high, and low. This is low, high, high. So if you can see that by this way, we are having 6 different states. Like this is one state. Okay, this is second state, the third, fourth, fifth, and sixth. So these are called different Hall states. Okay, so how to make the relation between back EMF waveform and the Hall sensors? You see this one. Wherever the flat top portion of the back EMF is there, I'm making here. Okay. Okay, this is the situation. So wherever the flat top portion of the back EMF starts, okay, it starts. You see, it starts. So there, your positive, like a Hall sensor gets high, and it continues until what? It continues until where? Where the negative flat portion of the back EMF is there. Okay, up till that one, because you're using 180-degree arc magnet. Understand? So here south, and here it is north. Okay, so this is the relation you can see there. So likewise for another phase, it will be there. Similarly, you can see this phase. Yeah, you see this phase. Okay, similarly for this phase, you can see that it starts from the positive flat portion. So by this way, you can see here that you have a 6 different Hall states. First thing is that, and whenever the Hall says a flat portion of the back of the starts, there the Hall sensor becomes high, and it continues until the negative flat portion starts. So this information we use it. So this is these are the 6 different states. So now we are knowing what is the relation between the back EMF waveform, back EMF, and the Hall states. Okay. Now, next, what we have to do? We have to inject the current. So to inject the current, we will have to operate the switches. Okay. So let's see further. So now, next, what we have to do? So this information we are knowing, Hall states. So please remember that this duration is of 120 degrees. Okay. And you remember that we have studied 180-degree mode of operation and 120-degree mode of operation of the inverter. So we are going to utilize 120-degree mode of operation of the inverter. Understand? So you see that according to this, like, because how many switches we are having? We are having 6 switches. Okay. So for your reference, I'm just drawing here the switches. This is switch 1, 3, 5, 2, 4, and 6. Like this. Okay. And these are the phases. Okay, so because three phases are there, so 360-degree divided by 120 degree. So phases are displaced by 120 degree. 6 switches are there, so 360-degree divided by 6, so 60 degree. So each switch will be turned on in the interval of 60 degrees. So switch 1 is on, on, and on. Understand? And because it is 120 degree, once it is on, it continues for 120 degree. We know this one. We have studied it. Okay. When we studied inverters. This is the situation. And for the rest of the duration, it is off. The switches are off. Switches are off for the rest of the duration. Okay. This is the situation. So now we identify, you see that when you give T1 high, means you are giving a positive current. And when you see that T1 is below is T4, when T4 is there, you see, when you turn it on, what will happen? Current will flow out from here. So it is going to contribute the negative one. Okay, for the negative. This is a positive current and this is a negative current for the phase. So this is, you see that how we are able to relate back EMF with Hall sensor and then with the operation of the switches. Okay, this is the relationship. Understand that one basic operation, like you can say that people can think when you are going to simulate it, how to do this one. So very simple approach is there. Just I want to say, what is the information available for us? Sridhar, we have time.
Ritesh, what I'm thinking.
Yes.
So, I mean, any important slides are there? Just finish off in 5-10 minutes.
Okay.
5 minutes, 10 minutes. Then we will go with the question and answers.
That will be better.
Yeah.
Okay. So I stopped that portion that in which I was to generate how to generate these pulses. So basically, we take the help of the information of AND gate and AND gate, NOT gate, and XOR gate. Sorry, OR gate. Okay. Okay. And then torque characteristic is there. So the torque is versus speed characteristic is there. So in this case, you will be seeing that you see that motor three-phase winding is there now, like this one. Three-phase winding is there. So each winding is having some back EMF induced, and then maybe some resistances. So it is represented as R, L, and the back EMF. Okay. So it is representation of RLE load. Okay. And then we are having the voltage source inverter feeding. So in practice, you will be seeing that we are having two types of voltages here. One, the voltage which is impressed by the inverter. This is O. So this is VAO, this is VBO, and this is VCO. These voltages which are applied by the inverter to the motor terminal. These are inverter voltages. And then there are motor voltages, like a voltage across the phase, VAN. Okay, this is phase voltage. This is phase voltage and this is phase voltage. This is there. And this VNO is also the motor voltage. VNO. So VAN, VBN, and VCN and VNO are termed as motor voltage, and these are the inverter voltages because you are going to apply this one through the inverter. Okay. So next, we go ahead. Just a moment. Okay. As I explained you before that, you remember that there I show you that only two pages are conducting. So power is EI plus EI. Okay, because this is minus E and this is minus I. So total 2 EI power is there. Okay. And we know that torque is equal to torque multiplied by omega equal to P. So just divide it P. So it is P by omega M. So it is, and E is just like the DC motor, K omega M. Divided by omega. Cancel it. So you can see that the torque is AI, which is like a DC motor. That's why the name is BLDC motor. And this is the speed torque characteristic of this BLDC motor. Understand? In this, you will be seeing that there is no constant power zone. Why? Because we do not have any field winding. Understand? No field winding is there. So no, we don't see that situation. Okay. Important, because now we are going to talk about the control. I will take 15 minutes. So you have this RL load. Okay, you see this one. Okay, so this you can write down the equation. You see that, let's say that is phase A current, phase A back EMF, and this NO, and this AN. So you can write down the rising potential, this VAO, and minus IAR minus L TIA by TT, and then minus EB minus VNO. And this VAO minus VNO is your phase voltage. This is very, very important equation for us, which gives us the dynamics of the motor. Okay, this is that. This is the equation. Equation is written here. Okay, this I explained you. Then with the motor, the problem is that when what happens that the current injection, what I have shown is a square wave in nature. Okay, this is square wave in nature. Okay, so when it is synchronized with a flat portion and is ideal in nature, we see that the torque is flat. But in practice, it does not happen. It deviates from this square wave nature. You see that? See that this one? This is like this, but here it is deviating. It is deviating. Understand? It is deviating. So because now the current is not ideal, the incoming current is taking some time to come in, and outgoing current is fall out. So it takes some time. Understand? So because of this like unbalanced situation, the incoming current and outgoing current, which should have been like this and this immediately, we see that the torque will ripple in the non-commutative. See that? Ripple. So this ripple in the non-commutating current results in the ripple in the motor torque. Ripple in the motor torque. So that's why that is a big problem, and because of that problem, your torque drops. Your torque drops. Okay, that's why in the previous slide you have seen that the dropping characteristic was there. This was dropping. Okay. This portion I better don't explain you. This I leave it because these are not that much important for our objective. Okay, this is not okay. You can see here that the motor torque is dropping down. And when you are running at a low speed, the torque can go up to 50%. But remember that this 50% with the low speed of the motor gets filtered out by the inertia of the machine. So you don't see this one. But at the high speed, you cannot filter out. So you see that the torque drops by much extent. Like this is the torque. Let's say that you see that a torque drops like this. Torque will be dropping like this. And this ripple can go to the 50% of the nominal. And if it is there, the life of the battery is going to get deteriorated. Motor performance is going to, you will not be able to utilize full of the motor. This is constant torque. It will be always good if you are able to utilize like this. Okay, so in practice, we are able to utilize around 60 to 70% here. This is a big problem, and we need to solve that only. So if you are having a very good control, you will be able to solve that problem. Otherwise, you listen the humming sound in the BLDC motor. If the torque ripple problem is not there, BLDC motor is very smooth. You will not listen any sound. Okay, these are some waveforms in which I try to show that the sinusoidal current is injected or square wave current is injected. Okay, and that control, I talk here about. Okay, I think we are going to conclude it. So you will be seeing two type of control in there. Either phase current control or DC link current control. You remember that I told you that at a time only two phases conduct. two phases conduct. So whatever the current is coming in from the DC link side, that goes out. So what was there? This is your phase A current, and this one is your phase B current. Phase B current here. Okay. So if you are able to control the DC link current, IDC link, okay, IDC link, that you will be able to control this. So this is the concept of the DC link current control. Okay. So all this I explained you how we generate the rotor position. Okay. Is how we identify that which switches are going to be operated. So 120-degree mode of operation, there's a relationship between the Hall sensor and back EMF. From that, Hall state is identified, and then as per the Hall state, we select the switches. Okay, and then we operate it. So this is schematic you can see here. You have the BLDC motor, this is the inverter, and this is your control circuitry and driver circuit. Driver circuit, and this one is there in the control circuitry. You set a torque reference, you know that torque is 2 Ki, so from that you get this ID reference, because torque divided by 2 Ki is ID reference. Okay, then you compare it with the feedback DC link current. You see that here it is, this is battery, and then you take the PI control, and then duty ratio limitation is there, and then you are able to control it. Okay. So this is what the DC link current control is there. Like actually for this we need more time, but it's okay. Like I'm trying to conclude it. This phase current control, in which we take the phase currents. Okay. But remember that for the low speed, this phase current control gives better performance. But for the high speed, both DC link current control and phase current control have the same performance. So you can work with the DC link current control. Okay. These are like some generations. We don't need at present this one. Okay. This also we don't need. Controller design is very, very important for us. So that's why I'm just going to explain how we do it. You see that just before we have written an equation, KVL equation. This equation we have written. So you have to take the Laplace transform. Okay. Take the Laplace transform. Then torque is there, take the Laplace transform, then back EMF, take the Laplace transform. Then you have the mechanical dynamics, Tm minus TL equal to J T omega dt. So again, you have to take the Laplace transform. Okay, and then we have to represent it in the term of block diagram. Okay, so then finally connect your block diagram. So this is the block diagram representation of whole of the system. But please remember here that when you are going to solve this complete circuitry, it will be very, very complex. Understand? You will not be able to design the PI controller easily. So what you do that there's a concept like if you are having two loops, one is, let's say, the back EMF is there, and another one is what? Current. This is the current. And what you are doing with the current? You are controlling it. You see, regulating it. So which loop is faster? This current loop is very, very fast than the back EMF. Understand? So when such a situation is there, without any issue, you can consider it as disturbance for you. You can neglect it for the time being. So if you neglect it, that this portion is not there, disturbance, and you are left with only this section. This PI, you see that PI, we know that it is represented as Kp plus 1 by a Kp by Pi. Okay, yes. Kp. Huh? This is what the PI controller is. This is same thing. Okay. So you are having this situation. Now from the closed loop, you can find out the overall transfer function is IAS by I references. Okay. So this is what next is explained. Okay. Yes. And then next thing is that you have to compare it with the standard equation. What is that standard equation? Numerator I'm not drawing. It is S square plus twice zeta omega and S plus omega square n. Okay, this is it. So you have to compare each of the term. Of course, you have to take it common. So it will go here tau E and tau I, and here it will be tau E, tau I, and here it will be 1 by tau E, tau I. Okay? And then this term will not be there. So you compare these two. So this whole term is equivalent to your twice zeta omega m, and this whole term is equivalent to your omega square. Then what we do that we decide what should be the bandwidth of your current control loop. Okay, this is what the bandwidth is there. And that is omega n is equal to 2 pi f bandwidth. Okay, so generally we keep it around 800 hertz to 1 kilohertz, something like this. Understand? So you can calculate omega n. So you are knowing omega n, and then damping ratio also we select. You can keep it around 0.8, 0.78 like this. Okay, so it is not like that you make heat and trial. Use proper thing, then you will be getting that. So you know now you can see that this equation is rearranged here. So you know that Kp gain is there and tau I is there. Integral time, time constant, that integral portion. So because this zeta is known to you, the bandwidth is known to you, so you can easily calculate what is the Kp and Ki value. This tau I is known, so Ki is Kp by tau I. Okay. So if you use this one, then you will be seeing that your control is very appropriate. Okay. So this is with the case only that what you say, square wave current is injected, and this is with the case when you inject a sinusoid. So this portion we have not discussed. Okay. So please don't make hit and try, because if it is not properly designed, that this ripple will be much higher. Understand? This will be much higher. We don't want that one, because if this is there, then you will not be able to utilize full of the constant torque zone of operation of the DC. Okay. So with this, I conclude this, and then let's go for the question and answers. Okay.
Yeah. Ritesh,
okay.
There are few questions are already there in the chat box.
Okay,
Otherwise,
I check one by one. Okay, I check one by one. Wait, huh?
Okay.
I stop this here.
There are,
okay, yes, I just start seeing one by one. Okay. Huh? Voice problem was there. Then clear. Okay. Can you explain the motor concept to install in a vehicle? See, you have the motor. The two types of coupling you can do. Either sometimes you see that we have a differential gear arrangement. So you can use that one. Some people use with this planetary gear system also. When you have like a central motor is there, and with that you are going to connect two different motors. So I think you are asking this question. Sorry. Please explain the motor concept to install in a vehicle. So BLDC motor concept, what we were discussing about. The battery become low, then how can you change the battery? So that is battery swapping. Okay. Otherwise, you have to charge the battery. So for that, you need a charger. Why don't you use that to charge the battery? Charge the battery, became a dynamo. Actually, what happens? See, you have that. What the energy is that you are going to recover the same energy. Okay. We definitely use the case of regenerative braking. So whenever the regeneration is taking place, we try to submit. You lower you are running at a particular speed, you reduce the speed. So regeneration will take place. So we recover that energy and submit back that energy to the battery through some power electronic arrangement, maybe a bidirectional converter. Okay. DCC, yes, you can definitely use it. And in old days that was being used, but nowadays we rarely use these things. Okay, because now the motors which are having we are available here, they have the control flexibility and everything.
It is, we have Dr. Rida Kunimangalam.
Yes.
Sir, you can unmute and you can ask the question. Dr. Rida? You can unmute. Actually, you're not unmuted. You can unmute and speak ask the question. Okay.
Okay.
I think he's
not there. Okay.
He's there, but he's not able to do
okay.
it. Anybody, other people
Meanwhile,
can...
I continue with the questions, and then
probably let them ask Ritesh, because I want to hear somebody's
okay,
voice
please
also.
ask. Okay.
Yeah, you can unmute and you can ask the question.
some connectivity problem.
No, I was. Is there any problem? Anybody not able to ask? You can unmute and speak.
Okay. ND.
That mute
Okay.
annotations, maybe we need to off from them, but
Okay.
okay.
No, okay.
So
Until
we,
like I continue with the other question, I think we will be able to finish it very soon.
yeah,
Okay. Then
yeah.
another question is that kindly tell me that electronics commutation of BLDC motor. Actually, that inverter, what it is there. Okay, voltage source inverter acts like a electronic commutator. Otherwise, like in case of normal DC motor, you have seen that the commutator, mechanical commutator was there. So what you are observing here, this voltage source inverter is acting like an electronic commutator. Kindly provide recorded video. Of course, Sridhar will provide you.
Yeah.
Okay, please provide recorded video. Okay. Uh, thank you very much. Okay. What is the difference between PMBL and PMSL? I explained you that both are same thing, permanent magnet brushless motor, and same name is that permanent magnet synchronous motor. Both are synchronous motor actually, because we have removed the rotor winding and in which DC excitation was there with a permanent magnet. So it, because no brushes is there, so it we say it a permanent magnet brushless machine. Okay, but it is the same permanent magnet synchronous. Say same synchronous machine in which rotor is replaced by a permanent magnet. So you say PMSM also. Okay, but in general, PMSM is we talk about PMBLAC. Understand? Okay. Can we use PMSM? Surely we use it. PMSM machines are used in EV or mid-duty vehicle. Understand? Like a 5 kilowatt, 6 kilowatt application, you can use it. Then what is the advantage? See, in different segment, different motor has different advantage. For low speed performance, it is a constant, like a light vehicle application, PMBDC have better performance than PMSM. Okay, but for high speed application like our mid duty vehicle, this PMSM machine has better performance than MLC. Okay, why we have trapezoidal shape waveform? Because we have made the concentrated type winding. Okay, okay. How do we design the logic of Hall sensor? Okay, actually, what happens that you have the Hall sensor HA, HV, and HC. So you can also generate not of that one. Okay, and then you use a AND gate. Okay, one AND gate, let's say one particular hall is 110. So you can give the input 1 from HA, HB, and HC is 0. So use a NOT gate and then give it. Okay, then it will be 1. So let's say 110 corresponds to hall state 1, and we, in that during that duration, let's say switch 6 and 1 is opening. So 6 and 1 will come. Understand? Likewise, there will be 1 and 2. Understand? So to get a gate pulse, you have to use OR operation of 6-1 and 1-2. Understand? So because 1 is common in 1, so you will be getting a high gate signal for switch 1. So this is a way how we had very short duration of time, short time. Otherwise, I would have explained this one. Okay. Which drive is most efficient in EV? I explained that it depends upon which segment you are working. For light vehicle, PMBLC is giving very good performance. And for very heavy, like for the truck segment, you have the only option that is induction. 2EI is the input power taken by the PLDC motor. Yes, this is true. Better, but battery going down. Okay, okay. PPT will be shared definitely. And which simulation software is best preferred to simulate? You can simulate it in eSIM. You can simulate it in MATLAB. Okay, you can simulate in any other open source software. So, but I used eSIM and MATLAB for the simulation purpose. Okay. Does free energy generation concept possible in electric vehicle? Yes, free energy generation concept is good. You can use it like a flywheel. Okay. Flywheel, which is a constant power source. So, no, sorry, it's used as a power source. We did not discuss because that comes under the category of supply system. So we did not discuss that part. Okay, so flywheel can certainly be used with free energy generation. Understand? Is there any difference between two-wheeler and four-wheeler principle? No, there's no difference. There's no difference. Okay, then questions. This BLDC system implementation is very costly when compared with the conventional motor. It is not costly. Very not costly. If in past days we were using a Chinese controller, so it was coming at the cost of 4,000 rupees only. Like individual is getting quantity in retail. In when it is produced in bulk, like you can think how much would be the cost? Maybe 2,500, 3,000, not more than that. Can you share the yes? Can you okay? Hall sensor logic do we have to generate back EMF? No, we do not have to generate back EMF waveform. Hall sensor, just we are concerned with Hall sensor. But yes, when you are going to run your motor or you're going to design the controller, it is always advisable that first you check the back EMF and then you check the waveform. And how we do this one? Just a moment. I think my screen is sharing, so I can explain you. Just a moment, huh? See, this is your motor. This is your motor, BLDC motor, and you have a winding here. So what you do that you make a star connection arrangement, okay, with a large resistance. This one. You can use this because we use this one. This is a very good arrangement. Keep the value of this one R very high, maybe in kilo ohms. Okay, and then what you do that because the problem is that you don't have the access of this neutral point. So how you will be knowing the back EMF? Because the representation is what? This one. And we are interested in knowing which one, what is the nature of this back EMF? Let's say this is A, this is B and C. Okay, this is A and this is not accessible. So for that purpose, you need a balanced star connected loop. Then what you do that you rotate this machine by your hand or by some mechanical arrangement, other arrangement. Okay, so because you're rotating it and you're not giving any supply, so what you will be observing here? Because the load is resistance is very, very high, it will be drawing very less current. So you will be mostly drop across, this will be negligibly small. So whatever the voltage you are going to measure here, means voltage means this voltage. Okay. This voltmeter. Yes, please.
Good morning, sir. Good afternoon. Good afternoon, sir.
Yes, Venkatesh.
This is Dr. Venkatesh BNMIT, Professor.
Yes, sir.
In fact, I was unable to unmute, so I have a couple of questions to you. Could you please?
Yes, please ask me.
If you take the battery management system, like we have a battery swapping technology is there, and DC charging is there, AC charging is there.
Yes, yes.
But initial investment, the cost is very, very huge. The question is the Indian scenario. When we may meet this kind of situations, we make at least 70 to 80% EV vehicles come to India.
Okay.
It's a big dream for India also. Like you take China or European countries or American countries, they're completely going into EV sector. When shall we expect even our India to reach this destination of maybe reaching 70 or 80% of EV vehicles in India, so that it's environment friendly and more advantages are there compared to gasoline vehicles as of now we're using.
Yes.
Even efficiency of the gasoline is around 25%. When we go for our EV vehicles, we can touch upon 80, 90 with the variations of the new technologies available.
Yes.
My question is, maybe my dream also come true when we may reach, because even government role is very essential here, maybe giving subsidy or with respect to manufacturing point of view. Can you please suggest us when shall we meet this destination point?
Okay, so actually you asked me multiple questions. Okay, like you talked about battery swapping also.
Yeah.
And then you talk about like how when it will be possible to reach that goal. So government has set actually the duration, the time deadline 2030.
Okay.
So all are trying to meet that 2030 timeline.
Okay.
The thing is that like what we can do and what government is doing. Government is trying to do its best. Okay. And what we can do is that to create awareness among the people.
Okay.
If we are like still people are in dilemma that whether we should uh, use this electric vehicle or a simple, let's say, scooty. So target, if like we directly target the light electric vehicle segment like this scooty and all those things, first we replace that one with the electric vehicles, because they don't need to run for maybe more than 60 kilometers in a day. And nowadays, all the like light vehicles like scooter and all these things, electric scooter, they are able to give us that much of range.
Correct.
So if we create awareness to convert that those scooter and all those things to an electric vehicle, that will be the first step. The next segment is that we can, because the people think that about the cars, whether we go to buy an electric car or that we work with that normal IC engine vehicles. Okay. Problem is that you cannot buy two cars at a home. Okay, you cannot buy. So the cost of that car is also high because of the battery.
Correct.
Okay, so if in the second stage, if we target about the cars, then it will be very, very good, because if you see that most of the contribution, you see that two-wheelers are there.
Yes, sir.
Okay, so my personal thinking that better first we talk about convert these all scooters to electric scooters. Okay, then and then it's a rickshaw also, e-rickshaw and all those things, small transportation. And the second thing is that we talked about this battery swapping. Of course, yes, this is very good for common people who are going to use electric vehicle, but this is a bit dangerous for investors, like those who are going to make the charging station. Why? Because suppose that you buy a vehicle of 1 lakh rupees, okay, and then maybe the battery cost would be 30,000 rupees. Okay, so let's say that your charging station is supporting 10 vehicles, so you have to make a arrangement for this 10. Okay, but remember that this is just like a gas connection. You come, take and use it. So for one vehicle, you need at least 3 arrangements possible. One with the vehicle, another is charging, and another is ready to use always. So again, for 1 lakh vehicle cost is there, and 90,000, you can consider it 1 lakh also. So one has to invest 1 lakh for one vehicle. So if you are having a facility of 10 vehicles, so 10 lakh you have to arrange. So each number of vehicle is there, that many investment will be the same. Investment will be of the same cost as that of the battery. This is the only concern at present. But if in future, like in near future, the battery cost reduces, this battery swapping will be an excellent idea, and it will be feasible.
Yes, sir.
So with that itself, like most of the problem of like range and anxiety, what we say, that whether we buy 2 cars or 1 car, that will be solved. So it will take a little bit more time, but of course that this is a good solution. And that we are having the fast charging strategies. So people are even able to demonstrate in 10 to 15 minutes charging. But of course, we are not talking about 10 to 15 minutes. Let's say you're driving for a highway, you drive for, let's say, 200 kilometers, 300 kilometers. Then if you are able to charge the battery for in 1 hour, because everyone takes a stop for at least 30 minutes or 30 minutes to 1 hour for food or other things. So if you are able to create a charging station which will be able to charge this vehicle in 1 hour, it's okay. People will be happy. So 300 kilometer, 1 hour stop, then again 300 kilometers. So that solution will be also better.
It's a fantastic information from your side, sir. Thank you so much. Sir. Thank you all the organizers. It's really a very good session. In fact, we were expecting more duration so that we would have got more knowledge transfer from your side.
Yes.
More knowledge transfer, maybe a 1 week seminar like that. Very nice, sir. Thank you. Nice talking to you, sir. Thank you so much.
Thank you, Dr. Venkatesh.
Okay, Sridhar, let me complete this one because someone has asked this question. So what you do that you give this output to your oscilloscope, okay, DSO. So you will be able to see the phase to neutral bottom. This is neutral and this is A. So what the voltage you are reading in your oscilloscope, it is your BAN phase to neutral, and that is nothing your back EMF. Okay, so you will be able to see this back EMF. It may be trapezoidal, maybe sinusoidal, whatever it is. And next, what you have to see, you have to see the Hall sensors. The Hall sensor output is also coming. So you take one output, Hall sensor output, and give to the DSO, okay, HA, and see whether it is getting synchronized with the back EMF or not. You have to see this one because you have to identify which Hall sensor is corresponding to which phase. So this information, it is must to first check. This is the first thing you have to check. Okay. But remember that if you directly check that motor, okay, Hall sensor, it will not be flat. Rather, it will be something like this. It will be something like this. Understand? Of course, with a power electronic arrangement, you will make it flat. That is another, some circuital arrangement, edge detection circuit and other things. So you have to identify this one. Once identified, you don't need to have the information of rotor position. Sorry, back EMF. You don't need it actually. But you have to identify for the first time when you are preparing your microcontroller. Okay. Let me see any other question is there. How reliable is the system considering the fact that it is, okay, see, electrical system, reliability of electrical system is very high. Of course, like there are some like fault tolerant system, like we try to ensure that our system should be fault tolerant. For those things, we have to make some arrangement. But in practice, this system does not have any problem. Feedback link, okay. Dynamo, okay, here this question is very good. May I know what is the effect of temperature on EV? Of course, yes, effect of temperature on EV is there. And that is mainly on the battery. Okay. Depending upon what is the operating temperature, life of the battery is decided. Like generally, life of the temperature, maximum allowed temperature is around 50 to 56 degrees. If you operate your battery always at 56 degrees, maybe you will lose your battery in less than a year. Okay, so you have to make some cooling arrangement also, whether it is during the charging or whether during the discharging. So temperature has huge impact.
Ritesh, before I forget,
Yes.
I see I'm an entrepreneur. So what is my duty is, in my place to get the employment opportunities for the engineers. Okay. How do you see this segment in the next 10 years? Because today morning I was just checking the news. In 2017, Nitin Gadkari have said that by 2030 in India, all the vehicles will be replaced with electrical vehicles. But today, the last month, his statement is revised that by 2030, probably 30% of the vehicles, automotive vehicles, will be replaced with electrical vehicles. He's still very much confident that there is a lot of, in the next 5 years, EV manufacturing hub is going to be a dominant industry in the Indian market. So how do you see this segment? I mean, like, do you really believe this, or is there any challenges in terms of technologically, and one is on the political fronts?
Political front, I cannot comment on,
okay,
because I'm a technical person. But okay, but from the technical point of view, yes, we have to look into multiple. Like first, a very good charging station should be there. If the battery swapping technology is being used, then the cost of the battery production should be very, very less. Okay, otherwise it is not feasible. Battery swapping is not possible.
But do we have that capacity in India now in terms of
Yes.
battery technology manufacturing?
Yes, people are working with the sodium ion batteries, then lithium ion battery cost is reduced. Like ISRO has done some research at that, but they are working. So
But
the
I
cost
heard
is reducing.
they're importing the cells from China and making the batteries in India. Is it the
See,
case, or are they manufacturing the
see,
cells also in India?
uh, see, it depends. Like for that, I cannot actually comment because I'm a application engineer. You can say.
Okay.
Okay. Of course, like lithium, if you see that it is highly it is available in Latin American countries. Okay, so anyway you have to import that lithium ions
Right.
from there. But people are also working with aluminum based, zinc based. Okay, that zinc based batteries, when they are going to come, then the range will be around 750 kilometers, one charge. and later you just replace the plate and again you run for the 750 kilometers. So technology is changing. Actually, chemical engineers are doing a lot. So as these things will come, and they're coming at a very fast rate. So when it comes, then adaptability will increase. Maybe like when it is revised, that we will be able to convert it 30%, but maybe in next 5 years it will be 70% or even more. So it is not like the 30. No. The rate is rising exponentially. So the
Even
responsibility is that
chemical engineers are working on the
they are working.
battery technology,
Yes,
and
yes.
we electrical engineers, where are we working?
We are working on the utilization, efficient utilization.
Okay.
Like
The drive.
You have a BLDC motor. You see that that same BLDC motor is there, but the problem is that we are not able to utilize its full of the constant torque zone. Okay, so due to that, we have to use a motor of oversized, the same speed. But if you solve those problems, then okay, a lower size motor is also good for you. Like battery is there. So if you are able to design efficient converters, then it is very good. If you are able to develop the fast charging strategies, it is very good. So this is from the technical front. And then another thing, we have to train the manpower also. Like because so many vehicles will be there, the huge opportunity is in the service sector of that one.
Okay.
The maintenance and everything.
That's true. That's true.
That's the
Already
most
that market
important
is
thing.
open, because now
Yes.
people are not finding the service engineers who can do the service portion of after the manufacturing. Because in Hyderabad we have quite a good
Yes.
companies like Electra is there, which is India's only bus manufacturing facility in Hyderabad.
Okay.
So that's a good thing. Like they are also finding, I mean,
Yes,
like
yes.
difficulty is there in terms of getting the manpower.
And like those who are working with the EV technologies, like they do not have any problem of getting job.
So
Okay.
now the trendy thing is EV,
Yes. EV means a
because
power electronics application for electric vehicle system.
okay,
So traction plus charging. Charging has good scope.
okay.
Charging, solar charging stations, and fuel cell based charging stations, all this. So if someone is working on the charging stations, charging technologies, it is also good because that is the most important thing. If that problem is solved, people will happily accept it.
But again, I feel the other side, EV is not a new trend in the world, because already our Indian Railways is running on the EV only. It's only
Yes,
that
this
battery is one thing is coming into picture, right?
uh, yes, the railway is online system, but nowadays even in case of electric vehicles also that online is coming. Online means like you are always connected with the grid.
True, that's a good thing. I think on along
Yes.
with the highway, I think they're planning from Mumbai to Delhi. In that highway, they're probably planning.
Yes, yes, yes.
There's one thing. So good. There are one more thing. Rajesh has asked like why people are calling PM BLDC, even though it's mostly that AC one. So one
See,
second.
motor is definitely AC. Okay.
Huh.
But the thing is that you have seen that the torque expression, what I have written, torque
Yeah,
is
yeah.
equal to 2KI. Okay. That is what similar to what the DC motor was there. Torque is equal to KI.
But
So this is
still,
the one reason.
people are calling it's more of a BLDC only, even though it's a PM BLAC, right? Is it that?
No, it is a PMBLDC.
PMBLDC, but mostly, as you said, like in the high capacity things, it's only PMBLAC, right?
Yes. And people don't say PMBLAC, rather people only say PMSL.
So that's good. And Imtiaz have one thing like, can you please explain about efficiency of PMBLDC? Is this motor better than the other type with respect to efficiency?
See, you see that here you do rotor, you have removed, the rotor winding is not there. Okay, you have used a permanent magnet. So that much of copper loss is gone.
So that means efficient, but only
Efficiency
high
is
capacity. It's not.
efficient. BLDC is not having high capacity, but BLAC, which was a PMSM, it has
Okay.
high capacity,
High capacity and
20 to 30 kilowatt.
efficiency wise, when you use a
It,
PM, then it's better, right? Because we are
efficiency is higher
right. The copper
because
loss will be less.
copper loss you are reducing it.
Good, good, good. So
Okay.
good. Any more? We have couple of questions, but you can unmute yourself and ask the question to take on priority. Guys, you can ask the question, Ritesh.
No, I actually audience have to ask the question.
No, I'm just telling them only
Okay,
that
that's okay.
Ritesh भाई को पकड़ना थोड़ा मुश्किल है.
No, no,
So it's slightly.
I'm always available. Okay, I just typed in my number. If anyone is having any
Yeah,
doubt,
yeah,
they can
you
directly contact me.
better you post in the.
Okay, I just posted here.
So Rajesh have one more question. What is the relation between temperature and permanent magnet? Though it is called as permanent magnet, but in reality, what is the life of permanent magnet?
Say, see that particular analysis I have not done, but uh, I started working with 2008 with a particular motor, and this is 2020, 12 years. Still, that motor is working.
Okay, but life-wise, probably, but it deteriorates,
So
right? I mean,
people say that like when the temperature changes, increases, that there's a possibility of changing the
demagnetization.
demagnetization. There's a possibility, definitely,
Okay,
but not a very short duration time.
okay,
Takes
okay,
longer time.
okay.
Takes much.
Imtiazji, do you have any questions? So good.
I think there
Good.
is no question.
They can unmute actually. Participants can unmute and ask. Good. Ritesh bhai, have you given your number?
Yes, I typed my number and email ID.
So wherein did you post it? Your screen is not visible.
No, in Zoom group chat.
But I am not able to see.
Say that. Okay, once again I copy paste.
Yeah, yeah. I can't unmute. Why people
Okay,
can't unmute?
okay. I post. Okay, once again I posted. Okay, that was sent to individual. Okay, now it is to common. Okay, then can we conclude? I
Yeah,
think
yeah.
there's
Let
no
us. I
question. I
think.
think.
Yeah, but there was some issue in. I think not able to. Okay, you unmute, Ritesh. So we'll
Okay.
end up the session now. Thank you, Ritesh, for all your time. And it's a wonderful session. And this is the first session in the HAW 100 webinar session, this series of webinars. So I personally got a little more excited because it's been a long time core technically involved session slightly, because in my regular front it's more of a it's a not more than technical, it's more of a non-technical stuff I'm dealing in the last few days. And I also got excited, look, why am I not doing in this kind of a segment. So definitely this kind of sessions would be helpful for everybody. And it's nice that all aspirants and all already working people already have done some groundwork and attended this session. Hope everybody got benefit out of this, and we'll be keep on doing this kind of a session. Please be a part of these kind, and definitely we will make it much more interactive sessions in the coming days. Thank you very much. Thanks for your time.
Thanks, Cesar.
Thank you,
Okay,
Ritesh
bye.
bhai.
Bye,
Bye
bye,
bye
bye.
bye.